So let's take a look at solving quadratic equations by graphing. Now, we don't really use table of values anymore. We complete the square, we find the zeros, we plot the graph, we look at the direction of opening and the vertical stretch and whatnot. But for here, let's just say that we begin by graphing this function, okay? So what I did here was I common factored out the x, and then I know when x is 0 and when x is negative 1, y is going to be 1. And then I found the middle of these two, which is negative 1/2, and I plugged negative 1/2 into here to solve when x is negative 1/2 what the y value is, and I've got it. So now what I'm going to do is I'm just going to point at where I've plotted these points. So when x is 0, y is 1. When x is 0, y is 1, because every tick is 1. Here's 3 and 3. And then when x is negative 1, y is 1. And when x is negative 1/2, y is 3/4. And there's our graph. Now, when we look at this graph, is it going to touch the x-axis? Absolutely not. So when we want to solve, we're going to say the answer is, just as we talked about previously, when it doesn't touch the x-axis, we're going to say there are no real roots. So here, solve, therefore, no real roots. All right, there we go. So now let's take a look at this one. Solve x squared plus 3x minus 4 equals 0. They want to know where it crosses the x-axis, where it equals 0, by graphing. So here, I common factored out. I know when x is 0 and when x is negative 3, y is equal to negative 4. And then what I'm going to do is first plot these. So 0, negative 4, 0, 1, 2, 3, 4. I'm just going to put a tick there for 3 and 3 so we know each step is a number, not two numbers. And then at negative 3, negative 4. So 1, 2, 3, negative 3, negative 4. We have another. So halfway in the middle is, of course, x equaling negative 1/2 or 1.5. And when we plug that in, let's get our y value. So let's see here. I'm actually going to use negative 3/2 because it's easier to do the work and simplifying with fractions. So y equals negative 3/2, negative 3/2 plus 3 minus 1. So negative 1.5 plus 3 is positive 1.5. And that times that is negative 9/4. And I'm going to make this 16/4. So now I've got negative 9 and negative 16 is negative 25/4. So negative 25/4, let's see, 4 goes into there almost 6 times. So this is a round, a little smaller than negative 6. So that means that halfway here, I'm going to go, that's negative 4, negative 5, negative 6, so like around there. The point is that because it's here, the curve is going to go like this and have two distinct real roots. Because if it was up here, it would have gone like that and had no real roots. So here we are, two distinct real roots. Now let's take a look at the next scenario. Here we have y equals x squared plus 6x plus 9. So when I factor this, I see now why it's called two equal real roots, because there are two roots that are the same. Even though we write it like this, we still, when we factor it and get the two roots, they are the same. So let's see here. That means we know what this graph looks like. This is a parabola shifted 3 to the left. So let's go here. 1, 2, 3. The direction of opening is up because it's positive. and that shows two equal real roots. Two equal real roots. Okay, let's try another one. Here, solve this. So first we need to rearrange it so it's in standard form. Bring the x squared over, bring the x over, and negative 2 is there, and nothing's left here. So now, what I'm going to do is I'm going to factor this. So let's see here. What multiplies to 2 and subtracts to 1 is, of course, negative 2 and positive 1. And so now at x equaling 2, just put a 2 there, and at x equaling negative 1, I have my two distinct real roots. And if I want to graph this, I know its direction opening up. So it's in the middle, somewhere here, and I don't even need to know exactly because I'm looking to just see, is there 2, 1, or 0 x-intercepts.